last week we stopped at the mesh analysis and super mesh. So I used the uploaded nodes in the spectrum. Okay, now which is we already know how to calculate the voltage or the potential, and also how to calculate the what we call a load. And then from the Kirchhoff law, whether KCL or KVL, we can get the particular values of I as request. As been asked in the question. Okay, so here we will continue with the node analysis. Okay, which is nodal analysis refer to the node. Okay, so what is node? Normally node when there is a branch of a current there. So for example, like in previous time in the lecture, last week lecture, this is the node. Okay, so this part is the what we call ground. Okay, and then we can calculate the voltage at this point or the voltage at this point. So depends on the question. Okay, so we go to note voltage. Actually, this is a quite simple technique, but the difficulty of this theory or this technique, how to determine the higher voltage and the lower voltage. So in other words, there is a difficulty for you to identify whether V2 come first or V1 come first. Okay, so why? Because we will check the potential difference between 2 points. Okay, so in this method, we can determine the voltage at each node, which is relative to the reference node. Okay, we can use the KCL. Okay, so when we talk about potential difference between 2 points, that means we will apply KCL, Kirchhoff current law. That means we will calculate the current. Okay, so V equals to IR. That means I equals to V over R. Okay, so when we talk about V over R, that means the V refer to the potential difference between 2 points. Okay, so that means potential difference. For example, like in this diagram, we will set at the lowest line as the ground. Okay, so the potential difference between A and B and the resistance across is 12 ohm. Okay, so when we write KCL, so the current at this element and the current at this element refer to the ground. Okay, not refer to the source. Okay, so we will set the lowest line as the ground. Okay, so and then from this equation or this method, we will have a set of question, okay, in which the unknown will be voltage at the particular points or nodes of the circuit, and then we can calculate the I or the V. Okay, depends on the question. So for this diagram, we can have a node at one point, which is N node. Okay, so from the Kirchhoff law, there is a potential difference between the source and the node across to R1. Okay, so and the potential difference between this source to the node and across to resistance 3. Okay, so and this one will be referred to the ground. So the voltage at the ground is zero. Okay, so that is the meaning of ground. That means the voltage at the ground is zero. Then we can write an equation of current at a particular node. Okay, so then we refer to the KCL, and then you will have the current across this element as I1 equals to VR1 over the R1. Okay, so in other words, you can start V equals to IR, then I equals to V over R. So for resistant 1, that means the voltage across R1 over the resistant R1. Okay, so that is for I1. So if you remember that when we calculate solve the problems related to the mesh analysis method, we set or we label the direction of I1, I2, I3, and I loop. Okay, so I hope you remember that. And then from this part, okay, so we can also use quite similar method, but we refer to the voltage across the node, and we should identify the ground. So that means this node refer to the ground. So again, I want to remind you that the ground would be zero voltage. Jangan ada value. So if you have value for ground, that is not ground. Okay, something is wrong with your calculation. Okay, and also for this node and the ground, the difference between this voltage, this point and this point, that means if you know the voltage, let's say V1 here at this particular end node, okay, so V1 minus G equals to over the 6 over ohm, because this is 6. And then another one is voltage from here to here and not, and then this one you can design as designated this current as I2 equal to VR2 over R2. Okay, I hope you're clear with that. Okay, so the next part is nodal analysis. The direction for the nodal analysis is arbitrary. Okay, so what does it mean? Okay, this one many times student will ask me, should we follow the terminal of the battery, or should we I mean, when I give the solution, and then the student said, oh, suppose this one from here to this point, okay, because this one positive, and then this one will be end up at here. No, that one is only for, the concept is only for mesh, but for node analysis is arbitrary. That means you can set the direction, you decide by your own self, but it must be consistent. Okay, so I show you what is the arbitrary means for this simple diagram, in which we have 12 and 6 volts, and then we have B point as the ground, and we have a point at where the current can be scattered, which is we can design that all the current out of the node. Okay, so when we set a current out of the node, that means negative R2, negative I2, minus with IR2, and sorry, I1, and minus with R3 equals to 0. So, or you can write as, this one is R1, so that means R1 plus R2 plus R3, it will be equals to 0, and then you define for each particular I. So for example, R1, okay, will be I R1 equals to VA or minus VC divided by R1. So our R1, oh, I have declined one, third decline. one student. I want to admit whether can alamak. Please log in back if I decline your request just now, sorry. Okay, because I'm using two computer here, one laptop is and one PC. So one PC for to admit your request. Okay, and then then we continue with IR1 R2, which is VA minus VB, and here VB is 0 over R2, and also R3 VA minus VD over R3. So the same thing if you set like this, okay, the right side. Okay, let's say I set R1 enter, R3 enter to the node, but R2 out of the node. So this one R1, okay. Okay, sorry Haziq. Okay, so can you check whether this equation is correct or not? Hmm? From the diagram, the label of the diagram is the current equation is correct or not?
The negative should be at R2, right?
Mm-hmm. Why? Out of the
Because
node, right?
R2, yeah,
So our equation would be IR1 plus IR3 equals to IR2. Is it correct? Okay.
yes, doctor.
Okay, then from there, okay, so from there you can define for each, yeah, correct, Jaman. In positive, out is negative. Okay, then you define each I. Okay, so for each I, you define the voltage over the resistance. Okay, and then you substitute to the I equation, current equation. Okay, this one I have uploaded in the lecture in the spectrum, right? How many of you do some revision on this part? Okay, so you should notice there is a mistake here, which is to test your understanding in and out. Okay, so for those who notice the mistake, that means you have a right concept of current in and out. Okay. Okay, so next part, I move to this part, which is the method how to do nodal analysis. So let's say we want to know the voltage, calculate the voltage at point A. Okay, so normally we will set a ground, which is voltage equal to 0, and then we identify the node voltage with respect to the reference node. Okay, so from here we have VB is 0 and VD is 6 volts and VC is 12 volt. So why 12 volt? Because there is no other element in between of this C and the source. So that means this C will supply 12 volt. The same thing goes to 6 volt. All right. And then as I mentioned just now, you decide which current is in and which current is out. Let's say you said that this voltage would be in, this current from this voltage should be in, and this one should be out. Okay, so from there you also can write like this, which is every node, every currents out of the node. Okay, so you can have KCL at this node as IR1 plus IR2 plus I3. okay, equals to 0, then you can define each particular current, okay, here, okay, ayo, okay, so here, then you define R1. Okay, so for example, you go back to this diagram. So this is point A, okay, and then the I R1 equals to V R1 over R1, and I2 R2 equals to V R2 over R2, and the same thing for the current tree. Okay, and then you can use V tail minus V tip. Okay, so because the voltage, we want to know the voltage difference. Okay, the potential difference between two nodes, 2 points. Okay, then we can have V tail minus V tip, or but you have to synchronize for all. Okay, so that's mean you can define I R1 equals to VA minus VC over R1, and I R2 equals to VA over VB R2, and I R3 equals to VA minus VD over R3. Okay, so just get the potential difference. But here you tend to do a mistake because when you mix tail and tips, you don't know which one should come first and which one is later. Okay, dekat sini. At here, the student tends to do mistake. So be careful because student can draw the diagram because given in the question, and then you just label again. But in some question, normally I will label directly, but student able to define the KCL at the particular node, and also define the I, because this one is only Ohm's law, but they find difficulties with the potential difference. Okay, so that is very common mistake. Okay, so that's why you have to be careful when you choose high potential and highest potential and lowest potential. So once you already know how to define the voltage difference over the resistor, then you can go to step 2, in which here you can find each value using the equation. Okay, so here, because we already know the KCL at node A will be I1 plus I2 plus I3, and then you define the voltage difference for each I, and then you will get the value of each. You just plug in the value of VC and VD and VB, and then you will get value of A from the solved equation. Okay, so I give you example here, which is we have a V1 over R1, okay, and VR2 over R2 for I2, and also for the I3. So this node, we want to know what is not voltage from the perspective of ground with respect to the ground, and then you will calculate this simple question, okay, about I using Ohm's law, which is I1 equals to VR1 over R1. And then you also sometimes you can mix with what we call mesh analysis, or you can directly use the potential difference using node analysis, and finally you will find the voltage node. Okay, so but this one is very simple. Okay, so you can look at this example later. Okay, so I want to stress on the circuit with two independent source. Okay, so two independent source, that's mean from this one we have voltage source and current source. Okay, so should be in a round shape, right? Because our round shape is a independent source. If we have diamond shape, then would be the case. Okay. Is there any question right now? Before I proceed, can you can follow? Still okay with you? I mean, the lecture you can follow. Can you follow my lecture? Okay. Then this one we want to determine the node voltage in the circuit. Okay, so first step is to get the KCL equation, which is you can have from the which dot that you want to determine. So that's mean let's say we have V1 here at the V1 node here, okay, or Vn or Vg, and also we set the lowest line as the ground, and then you will have V ground as a 0, and then you use Ohm's law to define I2, and then you will have this equation, which is VR2 over R2. Okay, this one is very simple. And then the current also, you define the current I1. Okay, so here I didn't draw the line of a current. So I hope you can draw in your revision version. Okay, so then you will know that VR1 equals to V1 over E. So E is the source of the voltage supply, and then you substitute into the Kirchhoff current law equation here, and then you get this equation. Okay, so here rearrange, and then you need to do some skill here, math skill here, and then you will get I1 equals to V1 1 over R1 plus 1 over R2. Okay, so okay, so then you can calculate V1 when you plug in the values of each parameter here. Okay, then the next part is about we want to determine the node analysis voltage using the impedance. So this is the continue from this part. Okay, then finally you will get I1 and I2 also. Okay, so here when we have two independent source but in the same type of independent source, which is we have current source, and be careful with the direction of the current sources. Okay, so again you will start with Kirchhoff currents law. Okay, so at which particular point you have to know, because you have to, the first thing you can label that the lowest ground as the lowest line as the ground, and then you have one node here, and then another node from second source here. Okay, so whether you want to put here or you want to put V2 here, okay, it's up to you. Okay, as long as did not across to the resistance R2, the label. You cannot put like put here. Okay, that is my I mean that. Okay, so you cannot put V1 here. So you have to put before the element, and this element should be in between of uh, one potential and ground. Okay, so from here you just follow the step, which is define this each particular what we call KCL equation, and then you can rearrange the equation like this. Okay, this part you have to practice. Okay, because the rearranging and expand the equation you have to practice. If you just look at this slide, there is a skip method steps here. So you have to expand from this equation, then you will get this equation, and then you can continue, and then you will get the value of current. Okay, So this one, okay, already using Cramer's rules also can, okay. Whether you want to use expansion method, or you want to use what we call matrix star, and then you can calculate IR1, IR2, and IR3 from the question. Okay, so eh, so that is nodal analysis. Very simple but tricky. Okay, so we already know how to calculate current and also voltage, and also I mean the element parameter using mesh analysis. So I hope at this point you can see the difference, mesh analysis and node analysis. Okay. So now my question: what is the difference? The main difference that you find for the mesh analysis and nodal analysis. Can you write your comments here? What is the difference? Difference between these two methods. Mesh analysis use loop. Nodal use nodal use not voltage, not voltage. Mesh use current loop. Okay. Nodal will use voltage at node. Okay, so that is the difference. Others, can you share what you have understand from this topic? Hmm? Before we proceed to Thevenin, our last topic. Uh-huh. No comments. Okay, so we will continue. Huh? Mesh analysis doesn't use Ohm's law, sure ke? Every every method will use Ohm's law. You cannot skip that. Okay. Nodal involve voltage, correct? While mesh involve current. Yeah, correct. And mesh analysis, we will refer to the power source, right? But in nodal, the current direction is arbitrary. Yes, correct. Okay, now these two analysis is applicable when we want to solve problems related to Thevenin's Norton theorem. Okay, so now I will introduce you about Thevenin's theorem. Okay, so Thevenin theorem, actually, when we have a long network of circuit, we can compress it until we get only one voltage source and one resistance with the terminal A and B. Okay, so let's say we have a set of a network let's say if you have five loops here. Okay, so the five loops there, you can summarize all the resistor as a Thevenin resistance. Okay, and then you can compress it or combine it, or you get the equivalent, you get the total of voltage as Thevenin potential. Okay, so be careful here because this is only a load. Okay, it's not counted in the circuit. Okay, so that's mean you have to be careful with the point or terminal that you refer to. Okay, for example, like in between of terminal A and B, the Thevenin should be looked in this way. Oh, so scary, my arrow. Okay, so Thevenin's theorem is resistivity circuit that can be consist of one voltage source and one resistor, in which this voltage source is known as Thevenin voltage, and the resistor is known as Thevenin resistor, and these two elements will be called or will be known is known as a Thevenin equivalent circuit. So as I mentioned before, if you have many loops before these two terminal, okay, so this loop we will summarize, we will combine, okay, until we get only one resistor and one voltage source. So this theorem with the aim to identify and separate a portion of complex circuit, okay, which is we call this as a sub network or sub circuit, and we replace with the equivalent Thevenin circuit, which is like this. Okay, so we will have VTH, which is refer to the open circuit voltage. So you have to know what is open circuit voltage. Okay, and if you look back at this equivalent circuit, the resistor and the voltage source will be in series. Okay, if Norton is parallel. Okay, so VTH is an open circuit. So when we open circuit, that means we remove certain things, right? And RTH is the input of the resistance at the terminals when the independent sources are turned off. Or in other words, we remove the independent source. So independent source, what is the label? Is it round or is it round shape or diamond shape? So you have to be careful with this sources, type of source. And then let's say we have here, which is we have V in, R in, and then this one is RL, the load, and then this one between 2 points here, and then we have sub circuit here. So we will evaluate the resistance from this direction. Okay. And also finally we will have these 2 points, which is RTH and VTH, and the load will be remain because the load is consists after the point of the reference, which is A and B. Okay, so there are two cases to consider the Thevenin's equivalent circuit or resistance, and then we will go one by one. The first case is there is no independent source. Okay, there is no round shaped symbol in the circuit. Okay, so we can directly get the resistance by remove any other sources, and then we will have VTH as the VOC and the RTH as the total resistance present in the circuit. Okay, the second case we have dependent. Okay, so for dependent, we remove all the independent source, and then we can get, plug in a value of for V naught or I naught, depends on the question, to the terminal, and we can determine. If you set a V naught, that means you should determine the I naught. If you set I naught, then you determine the V naught, because it depends on the how you set for the solution. Okay, so the RTH will be referred to V naught over I naught. Okay, and the same thing for this part, for remove all the independent source. And after you do the combination of the resistance, and finally you will get the equivalent circuit here. So that is all about the Thevenin theorem. So don't forget about the load resistor. Load resistor did not, influence the RTH and VTH. Okay, and also we can use other method, which is source transformation. So this one you already covered during your pre-degree course. Okay, about the source transformation. And lastly is about Thevenin and Norton. So as I mentioned before, Thevenin will be in series and Norton will be in parallel. Okay, so this is the apa panggil? Equivalent circuit for Thevenin, and then this one is equivalent circuit for Norton. So you can see this one, resistance and voltage in series, and this Norton for current, and resistance will be in a parallel. Okay, so we will see about the series and parallel. So I hope you remember how to calculate resistance in series, okay, and resistance in parallel. Okay, so which is for parallel is 1 over R1 or Rn, until you have many n numbers of resistor. Okay, so this one is a Thevenin equivalent model, in which we have RTH and VTH here. So when we have open voltage short circuit, that means the voltage would be 0. And then for Thevenin model, we will have ISC equals to VTH over RTH, which is referred to Norton. Okay, and also for Norton model, we can calculate V open circuit, and V open circuit is referred to the VTH, and this is how we want to relate Thevenin and Norton, which is VTH over I Norton over equals to RTH. Okay, so okay, so we go to the example. Maybe it's not clear for you to see only theory. So let's say we have two loops of circuit with the voltage source here, and then we can see the shape is round shape, and then you should know what is the type of the source. Okay, and all the values of this element is given here, which is R1 equals to 3 ohms, R2 is 6 ohm, and RL is 12 ohm. Okay, and then the first one, we want to calculate the Thevenin voltage. So if you refer to the voltage here, we will have the voltage across the resistance of R2, and then from this part we can calculate VTH equals to R2 over R1 plus R2 times with V1. Oops, ayo, tak padang. Okay, so can I? Okay. So when you have these values, okay, you should know. Anyone know why we use this formula? Hmm? Why we write this calculation? Why R2 over R1 plus R2? Correct? Potential divider. Correct? Okay, so why R2 over R1 and R2? How about, is it series or parallel?
Series. We want to find the voltage in R2.
Correct. Okay, so that means you have learned this one, right? In matriculation. Betul? Correct or not? Tak ngaku lah Okay. And then you will get 28 volt. And then you will, next step is to calculate the Thevenin resistance. So remember that we will look the circuit from this way, from the point A and B, not from the source. Okay, no, not this direction. If you look, try to solve the circuit using approach from the source is wrong. You should refer to this direction, which is between A and B. Okay, so RTH, I don't know why we need to do like this. I think you know better than me, which is whether it's series or not. And then you can calculate the resistance from this part diagram as 2 ohm. So now the resistance in series or not after we remove the source from the direction of A and B. Is it series or parallel? Ah. Okay, parallel. Okay, so in the next part, we go to Thevenin. When another approach that we approach we can do is when the load is in the between of the circuit. Okay, so what we can do, because we can see from this part, and then VTH and RTH, and then that's mean you have to consider this part. Okay, so second example, we want to find the Thevenin equivalent circuit and calculate the current that passes through RL and R when RL is 1 ohm. Sorry. So here we want to find the VTH. Okay. So refer back to my notes how we can calculate the VTH from this diagram. When we can plug in the values as shown in the red color, which is 10, 6, and 6, and low lines as a 0 volt. And the VTH is 3 over 5 times 10. And then we will get 6 volts. Okay, so the next part, if we want to find the RTH, and then we can redraw the diagram, and then we can short a voltage source, and then we can calculate as this RTH as this. Okay, so this one is quite tricky. Okay, which part in this diagram in series and which part of the resistor in parallel? Okay, can someone explain to me how we can determine which resistor is series, which resistor is parallel? Don't look at this solution from this diagram, because this solution is come after the diagram. Anyone? Jang, jang, jang. Hmm? How we can determine which part of resistor is in series? So this one in series, 2 and 3 in series, and this one in series. So you have to rearrange actually. To get better understanding, you rearrange. That means you can group this one as one series and then this one. Right? Or no? Hmm? Kenapa diam? Anyone can explain about this?
I can try, doctor.
Yeah, please.
Mm, if you look from the 2 ohm at the bottom, and then you go left, it breaks into two parts, the 3 ohm and 2 ohm. So if it breaks, I
Mm-hmm.
think it's parallel, the 2 and 3.
2 and 3.
It's parallel to each other because
Mm-hmm.
it breaks into two
So
parts.
that
So
means how many series circuit we have?
because we need to find the resistance from 2 ohm to the other side 10 ohm. So if you go from
Okay.
2 is series, and then it breaks into two parts. So that means 2 and 3 is the parallel part.
Mm-hmm. 2 and 3 is parallel part.
Hmm. I
How
mean,
about series part?
so if you find the resistance for 2 and 3 and you add to the 2, because 2 and 3 is actually series to 2,
Series to 2. Okay.
and then you
So
add,
that means this one.
yeah, 2 add with the parallel part of 2 and 3 and add to
Mm-hmm.
10.
So this one is parallel to this one.
2 is parallel to 3.
Right.
Only to the 3 part is parallel, 2 and 3 only on the left side.
Right. Kena. Okay. How about others? Okay, thank you. I think Daryl, right? Okay, how about others? Thank you. Siapa lagi nak explain? Hmm? Because after you remove all the sources, you only consider the original arrangement of resistor. But is a tricky part because it depends on how you understand series and parallel. Okay, so that's why in the previous slide I show what is the meaning of a series and parallel for the bulb, but will be applies to the resistor. Okay, so because if you um, wrongly rearrange this diagram, your result or your calculation would be wrong. Okay, so from this RTH we can calculate and define as the equivalent circuit like this. And if let's say RL is set to 1 ohm, then we can get the current value as 0.42 ohm. Okay, we also can calculate current through the 3 ohm resistor using source transformation system method. Okay, so in which you have to transform the source that are present in this circuit. So that means you can transform voltage to current to voltage source. So that is source transform. So you have to do one part by part to avoid the confusion. And then step one, we convert the source and then you get the current. So source would be in series, but current would be in parallel because comply to Ohm's law. And then from here, you also can solve this problem using KVL or mesh for last loop, which is the third loop. And then you will get the current flow to the I3 ohm. Okay, then this example, okay, we have one current source here. Okay, and then we want to find the VTH for this circuit. Okay, so if you see from this diagram, there is one part that you can use source transformation from the Ohm's law, which is V equals to IR, and you will get for this case as 5 volts. Okay, and then you can calculate the VTH after you remove all the sources, as I showed before, and then you will get VTH as 3 volts. So be careful with the arrangement of these 1, 2, and 3 resistors to make sure your calculation here is correct. Okay. So the next part, we want to find the RTH here, and then we know that we want to, when we want to find the RTH, it must be open circuit current source, and then the RTH would be like this. Okay, so again, be careful with this arrangement to avoid confusion. Okay, so this is how we calculate the RTH, and this one is the equivalent circuit. Okay, don't forget about load resistance. Okay, so this is another example actually. um, what happened like this? Oh, this one only. This one, okay. Hmm, tak boleh. Hmm. Okay, so this is an example when we have current and voltage source. Okay, to find the Thevenin equivalent circuit. So Thevenin equivalent circuit, I think you know that you should have one voltage, one resistor with the load. Okay, so this is the terminal of reference, which is between A and B here. When the first step, we can start with calculate the open circuit voltage of A, B. So you have to look at from this part. Okay, so you can use nodes analysis or mesh analysis, depends on your preference. So from here, we can have a node analysis, which is we use 10 minus V1. Okay, so this is the position of V. Don't say that you want to put a V here, okay? Because this one only source. Okay, so the potential between the, I mean potential difference between these 2 points will happen here, which is for the voltage, okay, not for the current. Okay, so 10 minus V1 over 5, why 5? Because only cross this part, and minus with V1 over 20, and this one is the ground part. Okay, this one is the ground terminal. So V1 minus 0 over 20, and then plus 2. So 2 is current, right? Which is from here. Why 2? Because if you see from this equation, actually is current. R1, R2, R3. Okay, so you rearrange the equation, and finally you will get V1 as 16 volts. So you already get the 16 volt. That means this one is open circuit voltage, right? So that is VTH, because VTH is open circuit voltage. So the second step, we want to find RTH, but we have to calculate the ISC first. So the RTH should be from the terminal A and B. Then you can find the ISC. So here, short circuit current. Okay, how we can calculate short circuit current? Because VTH we get from the open circuit voltage, and how we can calculate short circuit current? Hmm. I give you the homework actually to understand this topic, in which I skip how to get a VTH, but I give the value. In which finally, once you use VTH from the open circuit voltage and ISC from the short circuit, you will get RTH. So make sure you do this part, okay, this empty part to find the ISC, okay, as your preparation for for the test, final test, okay, final exam. Okay, so here is to find RTH. Why repeating? Oh, I think okay. For the same circle, and I think okay, I skip this one. I will remove because I think I paste a different circuit here. Okay, so this that is Thevenin, okay, and some of Norton. Okay, so I want to talk about source transformation just to flashback what is source transformation. So for the source transformation for voltage transformation will be in series, and for the current is only parallel. Okay, so you use Ohm's law to do the source transformation, and also depends on the type of the dependent source. The source whether is dependent or independent, but source transformation only applies to the source type dependent. Okay, so because you know that we can they will have constraint parameters, so you should carefully handle of this part. Okay, and we want to know about Norton theorem. So Norton and Thevenin is a cousin. Okay, because Thevenin will be in series, Norton will be in the parallel. Okay, so for Norton theorem, they will have a linear two-terminal circuit, which is replaced with the equivalent circuit in the resistor and current source. And Norton resistance will exactly same as the Thevenin. So here we have I Norton and R Norton. So you can see this is parallel type. Okay, so Norton theorem, we can calculate from ISC. So remember just now I asked you to calculate ISC. So from that part, you know what is Norton. Okay, so if we flash back, return back to this part, okay, as your homework, because I already solved VTH and RTH for you, but I skip for ISC. So this ISC will give you I Norton. Okay, so what? Okay, try to calculate ISC. Okay, so from that value actually ISC just now you will have a short circuit current. Okay, just now you remember that this part is the load for the Thevenin. Okay, so when you have I Norton, which is I short circuit just now that I skip, special for you to do, you can have from the Ohm's law as a VTH and RTH. So in other words, this one equals to I short circuit. Okay, can you see the relationship of the formula? Okay, then what else? Okay, with VTH, IN, RTH, we will find Thevenin and Norton equivalent circuit. And then you should know what is short circuit current, and you should know what is open circuit voltage. Okay, so if you have this part, you will have Norton and Thevenin. Because ISC equals to IN and IN equals to VTH over RTH. All right. So, any question? That, that is the last part of our lecture before we say goodbye. Mm-hmm. Any question? No question. Ah, very good. You understand. You understand actually, I know. But when come to the question, nothing. Huh? Can't follow well. Why, Anson? Ah, nah? New thing, okay? It's not new lah. It's very simple. Then looks. Mana tadi? Oh, in the part, huh? Okay, new for us. Okay, have to digest first. Yes, exactly. Try to do some exercise. Okay, now I want to share about okay, maybe some of you not yet okay, I prepare some movie. Mana pergi movie ni terlari. Right? Where is the cartoon I prepared? Okay, look at this. Kacau cepat pula. Kejap. Tengok dulu, you faham or not? You see first this announcement. Alright. Okay, so semua dah faham? Can you see the announcement just now? Is there any question related to the announcement? No lah. Penat tau I tulis. Mickey Ho, mana ada? Mana? Tengok balik sampai faham. Oh, ya ke? Okay. Part 1, 10 marks. MCQ, 30 minutes. Part 2, descriptive. Part 1 and part 2 is 30 minutes. Ni dia punya, oh this one. Okay. Ulang lagi sekali sampai faham. Okay, so as you know, there is no, mana muzik ni nak diam. Okay, there is no what we call apa tu, exam. Okay, so